Hysteresis property of magnetic substance is useful to make the permanent and strong magnets. A. Describe the formation of hysteresis loop in ferromagnetic substance. Let us understand what is hysteresis in brief. Okay, hysteresis is the phenomenon of lagging of magnetic induction behind magnetizing field intensity in a ferromagnetic substance or material taken through a cycle of magnetization. So I'm writing hysteresis is the phenomenon of lagging, okay, of magnetic induction, and we denote magnetic induction by the symbol B, okay, and it is the vector quantity, so I'm writing in magnitude, behind magnetizing field intensity, and we denote it by symbol H, and it is a vector quantity, and I'm writing in magnitude, okay, right now. In a ferromagnetic material or substance, okay, taken through a cycle of magnetization. So we have this, clear? And what we find is that magnetic induction B is directly proportional to magnetizing field intensity. So this is in magnitude. So we have this. Now let's understand the graph between magnetic induction and magnetizing field intensity, okay? So I'm drawing the graph. So what we find is that, okay, as H, that is magnetizing field intensity, is increase, magnetic induction also increases and becomes maximum or saturates, okay? So we find this. So let me write over here, clear? As H increases, okay, increases, magnetic induction B also increases. So we find this, okay, we find this, and it becomes maximum or saturates, okay? So we find this. So we find this, okay? And becomes maximum or saturates, okay? Saturates at, let's say, point P. So we have this. So this is P. So we have this, okay? Clear? Now what we find is that when we decrease H, so we are increasing H. So in this case, we are increasing H, okay? H is increased, then H is decreased, okay? So what we find, if H, okay, is now decreased, okay? After increasing H, B increases and becomes maximum or saturates, okay, at point P. Then we decrease H, that is magnetizing field intensity. Decreased. Then what do you find? B also decreases. So we expect this, okay? We expect this. After decreasing, we expect, or it is expected. So let me write in this way. We expect this. When H is decreased, we expect this path, okay? Initially from O to P, now from P to O. But this is not the case, okay? So we expect this graph to follow this path, but it do not follow this path. So I'm erasing this, okay? B decreases, but along path. So it follows this path now. Let's say this is Q, okay? It follows this path, but along path PQ. So we have this. So what we find is that when H decreases and becomes zero, then we find magnetic induction B is not zero. So we have this. So this is to be noted, okay? So I'm writing, but B is not equal to zero when H equals zero. It means that sample or material, okay? So let me write in this way. Sample or material is not demagnetized. Okay, it is not demagnetized. It is not demagnetized even when magnetizing field, okay, has been removed. So we have this because H equals zero mean that there is no magnetizing field. So we have this. Now, I'm redrawing the graph, okay? This is Q. So we have this. Now, what we find is that for H equals 0, okay, B is not equal to 0. So we have this. So what you find in this graph, for H equals 0, B has some value. So for H equals 0, B is not equal to 0. It means magnetic. So let me write in this way. It means magnetic induction, okay? Magnetic induction has some value, clear? And let the value of magnetic induction corresponding to H equals 0 be BR, okay? So we have this. So this is magnetic induction left in the substance after magnetizing field has been removed and is called residual magnetism or retentivity or remanence. Okay, so we need to understand this. Okay, so let me write over here. The magnetic induction BR, okay, left in the substance after magnetizing field has been removed is called residual, okay? So let me write in this way. It's called residual, okay? Magnetism. It is called residual magnetism or retentivity or it is called remanence, okay? So we have this. So this is to be noted, okay? So if I indicate this in a graph, so this represent, okay, in graph, this portion, okay? This portion in the graph that is OQ, this is called retentivity or it gives the value of retentivity. And we denote retentivity by the symbol BR, okay? So this is the magnetic induction left in the substance, okay? After magnetization or magnetizing field has been removed. So we have this, clear? Now, we want to reduce magnetic induction to 0, okay? So I'm writing in order to reduce B, that is magnetic induction, to 0, a value of magnetizing field, okay, intensity. So we can write in this way, a value of H equal to, okay, equal to, let's say HC. So we want to make B0, okay? So a value of H, that is magnetizing field, equal to HC must be applied. Must be applied in the reverse direction. In the reverse direction. So we have this in the reverse direction. So we need to apply H in reverse direction. So when we apply H in reverse direction, okay, then at H equals then at H equals HC, okay, at this value of magnetizing field, okay, we find magnetic induction B is 0. So we find this. So this value, okay, or this part of the graph, okay. So let me write over here. So this portion of the graph represent coercivity, okay. So let me write in this way. This is called coercivity. So we have this, and we denote it by symbol HC, the value of magnetizing field at which magnetic induction is 0 is called coercivity. So we have this. So let me write over here. This is called coercivity, okay, and we denote it by symbol HC. So we have this. Clear? Now, if H, okay, is further increased, okay, if H is further increased in the reverse direction, okay, B also increases. So we find this, and becomes maximum or saturates, okay, saturates. So let me represent this in graph. So when we increase H in negative direction, okay, so when we increase H in negative direction, so this is for positive. So what we find, this is for positive. So when we increase H in negative direction, then B also increases and saturates, okay, it saturates at, let me write in this way, at point, let's say R. So we have this. So this is R, okay. So we find this. Okay, we find this. Now we again decrease H in another direction. So we now decrease H, okay, in reverse to this condition, okay. So what do you find? On decreasing H again, okay, in another direction, B, that is magnetic induction, follows path, okay. So it follows this path. It follows this path. So it follows this path. Clear? It follows this path. Let me draw in this way, okay. So it follows path R. Let's say this is X. this is X, okay? And this is, or let me draw directly first, and then I'll explain it, okay? So it follows this path. Rx, this is F. So we have this. So what we find, B follows path R, X, F, P. So we have this. It follows this path. Clear? It follows this path. And closed curve, okay, is obtained for the complete cycle of magnetization. For the complete cycle of magnetization. Okay, so we have a one complete cycle. So this curve or loop is called hysteresis loop. So we can write this curve or loop is called hysteresis loop. So we have this. So we are asked to describe the formation of hysteresis loop in a ferromagnetic substance. So this is how we explain the formation of hysteresis loop. And when we come into question C, explain the coercivity and retentivity of hysteresis loop with appropriate diagram. So for question C, okay, we can see this value of magnetic induction, that is BR, is called retentivity, and in graph we have retentivity, okay, shown, and this value of magnetizing field, that is HC, is called coercivity. So we have this for solution of question C also, okay. Now solution B, okay. Explain the nature of hysteresis loop given by soft iron and steel. What does this loop signify? So nature of hysteresis loop given by soft iron and steel. So we have this. Okay, we have this. So this is hysteresis loop. Clear? And we need to note that the area, okay, the area within the BH curve. So this is very important concept, okay. The area within the BH curve or loop represents the energy dissipated, okay, per unit volume in the material through a cycle of magnetization. So we have this. So the area within the BH core represent energy dissipated per unit volume in the material taken through the cycle of magnetization. So let me add this also. Taken through a cycle of magnetization. Now we are asked to explain the nature of hysteresis loop given by soft iron and steel. So for this, okay, let me draw the hysteresis loop for soft iron and steel, okay. This is for soft iron, okay. This is for soft iron. So we have this. So let me. This is for soft iron. And for steel, okay, we have this. This is for steel. So we have this. So this is what we get for soft iron and steel, okay. So what we can see is that, okay, what we can see is that this is retentivity, okay. This is retentivity for soft iron. So this is Br for soft iron. So I'm writing in this way, okay, Si. So we have this, and this is retentivity. This is retentivity for steel, okay. So I'm writing in this way. So let me write over here. Br Si. This is retentivity for soft iron, and BRS, okay. This is retentivity for, okay, steel. So I'm using this symbol, okay. So we have this. And when we compare coercivity, okay, so what we find is that, okay, this represent, okay, this gives coercivity for, this is for soft iron, okay. So I'm writing in this way, Si, and this represent, or this point represent coercivity, that is Hc for steel. So Hc, Si, this is coercivity, okay. For soft iron. So we have this, and this is for steel. So when we look into this curve, okay, what we find is that, okay, so I'm writing retentivity, okay. Let us compare retentivity. when we compare retentivity, what we find? Retentivity for soft iron is greater than retentivity for steel. So we find this. Okay. Now let us compare coercivity. Okay. So when we compare this, then we find coercivity for steel is greater. We can see it is greater than coercivity for soft iron. So we need to understand this. Okay. So I'm writing over here. Okay. Coercivity of steel, we can see it is very high. Okay. Is very high, and retentivity is also large. We can see retentivity is also large, though it is small in comparison to the retentivity of soft iron, but it is large, fairly large. Okay. Therefore, steel is used for making, okay, for making permanent, okay, magnet or magnets. So we have this. And what we find is that for steel, the area is large. So we need to note this also, okay? So I'm writing, even though the area, okay, the area of steel is large, it does not matter because area within the BH core represent energy dissipated, that is loss per unit volume, okay? So I'm writing, even though the area of steel is large, it does not matter, okay? It does not matter because permanent magnet is not taken, it is not taken through a cycle of magnetization. Through a cycle of magnetization. So this is to be noted, okay? And let me erase this first. When we look for soft iron, okay, in the BH core, the area is small for soft iron, okay? So I'm writing, area is small for soft iron, okay? It is small for soft iron. Therefore, it is used for the core, okay? Because when area is small, then energy dissipated or loss per unit volume will be small, okay? For the cores of transformer or transformers and generators. So we have this. And due to small coercivity and area of soft iron, it is used for making electromagnets. So I'm writing due to small coercivity, okay, and area of soft iron, it is used for making electromagnets. So we have this.